of some of the work that we've been doing over time, updates on things that have been going on for a long time, and ended at that. So we're going to start with some of our long-term drainage work, which happens to take place at this Kelly farm. You see a satellite, or actually an airplane view of it here. These are 24 plots. We usually have 6 different treatments going on here. They're all individually tile drained, so we're looking at the impact of those different treatments on water quality and crop yield. One of the things we've been doing there for 17 years now is 4 of those plots do have a Woodchip Bioreactor installed on them. It'd be a bio curtain, if you will, or where the tiles are surrounded by wood chip filled trenches. And here I'm just showing the blue is what's coming out of the conventional drainage as far as nitrate concentration every year, and the red or brown there is what's coming out of the bioreactor. As you can see, that ever since 2001, the entire project, the bioreactor's been working very well. And here 17 years later, although the total nitrate coming out of the field is less, we're still removing quite a bit, and the last 2 bars there are the averages over those 17 years. And so we're removing well more than half of the nitrate is coming out with the bioreactor. So after 17 years, it still seems to be working as well as it did today, day number 1. So I think that's pretty encouraging for the Woodchip Bioreactor. We've also been looking at cover crops here for 17 years, and we're seeing kind of the same result. Again, the blue bars are the conventional drainage without cover crop, and the brown would be the cover crop. Everything else is the same on those treatments, and you can see every year that we're getting a lot less nitrate coming out of the cover crop other than the first year, 2001, and that was because we had problems getting a cover crop established in 2000. But other than that, you see that we've been doing a pretty good job. And again, the bars there on the far right represent the average over that time. So again, the cover crops are removing more than half of the nitrate that's coming out of these, that would be coming out of the tile drains under conventional corn soybean rotation. As Matt said yesterday, we're starting a new project there, combined a FireFR project where we're looking at different farming practices, kind of your business as usual and aspirational practices. I'm not going to talk about any of those treatments, but one of the things that we've been doing there now is not only do we measure nitrate coming out of our tiles, but we're looking at ammonia, total phosphorus, total dissolved phosphorus, and we're looking at potassium and sulfur as well. And so I'm just showing you here the average results for last year for all the treatments together, so no treatment effects being shown here. Just to give you an idea as what we're seeing there as far as the top there is concentration, so the mean for nitrate, we're almost seeing no ammonia coming out of these systems. Most of the phosphorus comes out as total dissolved phosphorus. Seeing very little potassium as you'd expect, since it's a positively charged cation. We're just not going to see it coming through the soil very fast. And a lot of sulfur, though. So sulfur kind of surprised me that we're seeing quite a bit of sulfur coming through. We haven't got the plant data back. Of course, we're removing a lot of NPK in the grain as well. Don't have those numbers yet, but as far as losing things out the tile, we're not really seeing much potassium. Not seeing much phosphorus here either, although those would be perhaps important concentrations there. And then one other kind of interesting thing for people to contemplate, we have a zero nitrogen treatment going on there, and this is the results from these bar charts here, the results from that. Starting between 2011 and 2012, 2012 would be a corn year, we put no nitrogen on that treatment. And it's been in corn soybeans since then. We don't put any nitrogen down on that treatment since the beginning of 2012. And so we're going from the positive years, the even years are corn, odd years are soybeans. And it's kind of interesting to see that going from 2010 to 2012, we actually saw a lot more nitrate coming out of the zero-N plot than we did 2 years earlier than that. That's probably to be explained by weather, perhaps. But it's kind of a stepstone kind of pattern there that I thought was kind of interesting. We're going from slightly higher in 2012, and it dropped in 2013, which is the soybean year, was back up in 2014, which is the corn year, back down in soybean, but slightly downward trend as we go. But you can see even after, was it 5 years or 6 years, we still haven't drawn down the nitrate out of that plot by putting no nitrogen on and having a corn soybean rotation. But it looks like we're getting a little of sequestration from the soybeans, because the next year in the crop we're losing a little more nitrate than we do under the soybean year. So it looks like the soybeans are adding a little nitrogen, as you'd expect, through into the soil each year. And so it's kind of an interesting pattern, but it shows you it takes many years before a zero-N treatment is really acting as a zero-N treatment, I think. We're going to move on to saturated buffers. Just to give you an update here, we're showing, I don't know how many field, it's like 19 field year results here, where this is percent of total N load. The blue bars represents how much is being removed in the buffer, so any nitrate that goes out into the buffer, how much of that's being removed, and the average there is 84%. So if we get the nitrate out into the saturated buffer, we're removing about 84% of that nitrogen. The red bars represent how much water coming out of the tile outlet we're actually able to divert out into the buffer, and that's averaging about 50% over all these different years and different systems that we've been monitoring over time. So about 50% is being diverted. Of what that's diverted, about 84% is being removed. And we're up to, we're monitoring 11 of these systems right now. We're hoping to put 10 more in this spring and summer. So we'll have quite a few of these within the state of Iowa that we'll be monitoring. Maybe I'll skip that graph. It's a little complicated to describe. One of the things that we're trying to look at is what explains the nitrate removal in saturated buffers. And kind of the best thing that we've come up with so far is to get the length of the buffer, so the pipe size of the buffer. It's anywhere from ours, it goes anywhere from like 300 feet to about 1,500 feet are our longest ones. And you multiply that by the area that's being drained down to the outlet. So that's that pipe length times area that you see on the x-axis. That seems to be our best predictors as to how much nitrogen and as pounds or kilograms is being removed out of that from that saturated buffer. So that's kind of an interesting relationship, but it's been our best way of explaining how much nitrate we can remove out of a potential saturated buffer. One of the questions they've always asked is, in a saturated buffer, are you replacing a water quality problem with an air quality problem? Because we're trying to denitrify that nitrate in the riparian buffer, and during denitrification, if it's not all the way to completion, you're getting a little N2O coming back out of it. Of course, N2O is a very powerful greenhouse gas, and so that's been a concern over time. And I can pretty definitively say today that no, we are not doing that. And this is research done by Morgan Davis, who was here last year. He's finished his PhD, and he's got a lot of work looking at nitrous oxide emissions from saturated buffers, normal riparian buffers, and crop fields. That's kind of summarized here. The regular buffer on your right, we're losing about 3.8 kilograms of nitrate per year coming out of there. The buffer on the left, the middle one there, the 3.9, that's your saturated buffer. So almost no difference between a normal riparian buffer that you might be putting in versus a saturated buffer. And the 14.1, that's what's coming out of a corn soybean rotation. So if you didn't have the buffers there and you're farming right up to the edge with a corn soybean rotation, you're going to be losing a lot more nitrogen as N2O than you would be if you just put in a regular buffer. And then if you make it a saturated buffer, it's almost no different. So we're actually, if you put in a buffer, you're doing, it's a positive impact on nitrous oxide emissions. Another question that we had asked as well, we think that most of the nitrate in a saturated buffer is being lost through denitrification. We don't have real good evidence of that, but another graduate student, Tyler Grove, was in there and taking soil cores out of the buffer periodically over time and looking at the natural denitrification potential within that soil itself. And then he's taken that and kind of multiplied out what those cores would be telling you as far as the capacity of denitrification. We have three different saturated buffers here, the BC1, BC2, IA1. The two on the outside actually have a well-established perennial vegetation on them. That BC2 site was actually going into a site that was in corn and soybeans. We put in our plumbing, and then we've established a perennial vegetation on top of that. So it's a pretty new saturate or perennial buffer, if you will. But you see with the green, it's really it's a messy slide, I understand, but basically what he found is that 3 out of the 5 years, or 3 out of the 6 years that he's got here, is that denitrification, as he measures it with the cores, would account for all the nitrate that's being lost in the saturated buffer. So you could say that, yeah, okay, denitrification potentially could take care of all the nitrate loss that we're seeing. But in the other 3 years, especially in that one in the middle there, something beyond denitrification has to be taking place, because at least as far as taking the potential denitrification with the cores, we're not able to account for all the nitrate loss that we're observing as the water goes through the buffer. So something else going on, probably sequestration of that nitrate into the plant root, into the plant itself, which will come out sooner or later as our organic nitrogen. I believe, oh, then we got my, oops. This is a video, but I don't know if I can even get it started on, apparently we don't have the, there it is, okay. Other question that we have, and I'll just run this while I'm talking, is you put in a perforated pipe into a buffer, are you going to be getting it plugged up with roots over time? And so this is just a camera view of the one that we've got that's been in now for 7 years. So this is a saturated buffer that's been in for 7 years. And you can see that, yeah, we are getting roots in them. There are sections where they're very clean, but we do see some roots coming in. In my observations of this, we've got, I got hours of this stuff if you want to watch it. It's kind of fascinating what you find in these things. Sometimes you'll hit some tiles and they're full of crickets and centipedes. I don't know what they're eating down there. This one, you don't see a lot of insects. You see a spider web every now and then. But this is during dry. Obviously, there's no water going through them right now. You see we're getting through some roots, and then we'll get into a clear area. But from my observation, it looks like the roots that are getting into the tile are coming in as they grow down vertically. They hit the tile, and then they penetrate in through one of the perforations to get in the tile. I'm not seeing a lot of where the plants are coming down, or the roots are coming down to the sides or the bottom, and then growing into the tile itself. So it looks like one of the solutions to this issue would be to have no perforations at the top of the pipe. So I'll get that back to the drainage industry. But what we really need is a pipe that's only half perforated on say one side and not on the top, and then we can lay it down so that the top is non-perf and the bottom's perf. The other thing we thought we'd be doing is we trench these in, we can lay down the tile and then maybe just cover it with a plastic sheet or something. So when the roots come down, they hit the plastic sheet and it will go into the tile. It looks to me like that might solve 90% of our problems as far as root plugging in these tiles. And of course, we haven't had anything actually plugged because we're not seeing these roots detaching and flowing down and forming a big clog in the pipe. But we are getting some roots into the pipe. So anyway, the challenge to the industry, I guess, is can we get up to some technology here where we can get the pipe where the perforations are only on the the sides to the bottom and have it solid on the top. And I think it would probably take care of all the issues that we're seeing so far on these. And that's it. So we got a question already.